Okay, let us go for the last lecture of today, and so I just want to prosecute a bit of what I said in the previous lecture. So this was about the continuity and the monotonicity and limit. So and it's also related to monotonicity and continuity. And so here what I want to tell you is that, of course, there is another symmetric theorem for monotonically decreasing functions. I write here the statements, and the statement is very similar to the one I just gave you. And again, monotonicity and limits, I would say 2, and it is on right limits. And this time again monotonically increasing, and I consider x bar in DE, which is a accumulation point, but in particular it will be a right accumulation point. And we have that then the limit for x going to x bar plus of f of x is this time the infimum of f of x, x larger than x bar. Let me read it again in order not to make a strange mistake. So in R, f from E to R monotonically increasing, let x bar in D such that for every W blah 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 blah. Right accumulation point, then this is the right, and x larger than x bar, and this time it is the infimum. And let me consider the picture here. Picture here is very simple. Again, the function is monotonically increasing, but this time we are taking the limit from the right. So we go towards x tilde. And you see, when you go towards x tilde, you are declining here. We are going towards lower values, and this is why at the end you find the infimum. So since you have many cases, you can easily get confused here. In order not to get confused, always think of pictures. Okay, pictures really help a lot in these cases. And of course, there are two other theorems exactly in the same spirit, and I want to give you all of them. Monotonicity and limits 3, which means this time you have monotonically decreasing function. Increasing, we already exhausted all of that. So decreasing function and left limit. Okay, here situation is the same because function okay as usual, and then we have a left accumulation point, and this is correct. And now I want to take the left limit and just draw a picture, a small picture, in order to understand what happens here. So the function is decreasing. So it is like that. And when you perform the limit from the left, you go this direction, so you accompany the function down towards lower values. So instead of the supremum here, you will have the infimum. And now, let me give you the last theorem of this family, the fourth. The fourth theorem is with decreasing function and right limit. Well, okay, here I forgot to correct here. It is not increasing, it is decreasing. And here again, I want to study a decreasing function, but I want the right limit to be computed, so x bar accumulation point, but accumulation point from the right, especially from the right. Okay, this is a right accumulation point, and here you have x bar plus, and this is larger than x bar. So let me check by a picture as usual what is the result, whether it will be the infimum of the supremum to occur as a limit. So picture can help us. Again, decreasing function is like that. It's not very interesting to write down functions with discontinuity or jumps at x bar. Okay, also continuous graphs can play the game very well. So here I have x bar. I want the limit from the right. And again, you have to follow the function from the right this way, and you are climbing up, so towards higher values, so supremum is good. Okay? And so you can also imagine to use a table like this. And here, in this table, you have here what is the function, what the kind of monotonicity, the kind of limit, and here the result. So here you can write what is the monotonicity limit, the result. Size of column is a bit too large, but the monotonicity of the function is increasing, for instance, and the limit is the left, increasing left limit, and the result is the sup. Monotonicity increasing, limit is the right, and then you have to take the infimum. The monotonicity is decreasing, the limit is the left limit. Think of it, left limit, so you go towards the infimum again, and you have decreasing monotonicity and right limit. So you got the sup again. This is just a table for people who like tables. I don't like tables very much, however, because you have 4 different situations, and for every situation you must be able to choose the supremum of the infimum. But remember, instead of studying it by heart, think of the picture. The picture helps you very much. And there is a last theorem I want to give you. As it's a nice theorem. I like it very much, but I will not give you the proof because I think it is quite difficult for this course, but it is a nice proof. So, another theorem about monotonicity on interval and discontinuities. You have f, which is a function whose domain is an interval. This is very important. The interval is AB, so f from AB to R. A monotone function. I don't want to specify whether it is increasing or decreasing. Then all discontinuity point of f are of the type jump and they are at most countable. So they cannot be an uncountable set. The set must be at most countable, either finite or empty or countable. Okay? And I don't give you the proof. And without the proof, it is quite difficult to understand what does this theorem says. And the idea is that try to introduce discontinuities, and these discontinuities are always of jump type. Why jump? Because here you cannot go to plus infinity here, because otherwise you cannot continue the function here. And also here you cannot go to minus infinity because you must stay above that. Okay? The point that it is difficult to understand is that the number of these discontinuities is countable. So, but okay, if you understand it well, if you don't understand it, don't think of it. It is not so important. More important probably is to give you an example of a function with an uncountable set of discontinuities. This is a very famous example, so I ask you to remember it, because it is f from 0, 1 to r, or you can extend it to r, that associates to every x 0 if x is rational, 1 if f(x) is irrational. So f is discontinuous, so it's not continuous. Let me say it's not continuous. In all points of the interval 0, 1. And I ask you to prove it Now you must be able to do that. It is quite easy to prove it. This F is called Dirichlet. Some people say Dirichlet, but it was German. So probably the correct pronunciation is Dirichlet. So this is the Dirichlet function. And so it has an uncountable set of discontinuities, because all points in the interval 0, 1 are discontinuity points, and 0, 1 is an uncountable set. The last thing I want to stress, it is very important again, it is a remark. The remark says that let F, again, let E in R, X bar is an accumulation point of E, both from the left and from the right. So such that for every W, or for every V in U X bar plus, V intersection E minus X bar is not empty. And for every W in UX bar minus, W intersection E minus X bar is not empty. So it is possible to perform the limit for X going to X bar both from the right and from the left. Then we have that the limit, I forgot to define a function from E to R, for instance, monotonically increasing. Then the limit for X going to X bar from the left of X is not larger than the limit for X going from X bar from the right of f of X. Indeed, taking X, Y in E such that X is smaller than X bar, smaller than Y, by monotonicity we have f of X less or equal than f of Y. Then take the supremum of the two sets. We have the supremum of f for X less than X bar, X in E is less or equal than the infimum of f, X larger than X bar, X in E. And by the theorem we know that this is the limit from the left, and this is the limit, X going to X bar from the right. Okay? So this is an important relationship. And the last thing I want to tell you is just to prove the theorem, the first of the theorem on monotonicity and limits in the case psi equal to plus infinity, because I did not do it. Okay, see you on Tuesday for question time.